Good morning, students. So in the subject MEMS, we have started the unit number 5, that is mechanics of solids in MEMS. So in this we have seen the MEMS three-dimensional structure. So for that, the engineering mechanisms involve solid, fluid and thermomechanics. Then we have seen the basic concepts, that is Newton's law of motion, equilibrium, stress and strain. So we have seen the definition of stress, then types of stresses, then we have seen strain, again types of strains, then relationship between the stress and strain. Then we have seen Hooke's law, then we have seen Young's modules. Then last time we have seen the Poisson's ratio or Poisson's effect. So last time we have started with the linear thermal expansion. So already we have seen, if we are going to deal with the electronic components, then it is used in automotive, communication, aerospace and other industries also. So miniaturization with higher package density and accelerated development process, which is having the great impact on the reliability of electronic components, because rapid changes of ambient temperature or maybe there is internal production of heat may occur during the operation. So may create high thermal stresses due to the mismatch of the thermal expansion coefficients of the different materials in electronic components. So for example, we have seen the gold and silicon, that the thermal expansion coefficient is given here. Then we have seen that the thermal expansion is the physical property of a substance, gas, liquid or solid, so to modify its shape, that is length, area or volume. So function of a temperature. So thermal expansion relates with the expansion and contraction of particles in a substance function of temperature. So thermal expansion can also be regarded as a fractional change in size of a material per substance, so caused by a change of temperature. So thermal expansion has effects on gases, liquids and solids. So from the mathematical point of view, thermal expansion can be described as, so it is linear, that is one directional, 1D, aerial, that is two directional, 2D. So volumetric, so three dimensional, that is 3D. So the linear and aerial also called a superficial. The thermal expansion applies only to solids. So the volumetric, that is also called as cubic, thermal expansion applies to both sides of both solids and liquids. So for gases, thermal expansion is described by the ideal gas law and it is treated differently. Okay, so thermal expansion has effects on gas, liquids and solids. So from the mathematical point of view, thermal expansion can be categorized as one dimensional, two dimensional, three dimensional, that is linear, aerial and volumetric. So linear and aerial thermal expansion applies only solids if the material has the solids, and volumetric is applied to both solids as well as the liquids. And but for that the ideal gas, that is ideal gas law is used. So linear thermal expansion. So here this is the original length or initial length, and delta L is that are the change in length. So linear thermal expansion applies mostly to solids. Okay. So knowing the initial length L0, of a given solid. So for example, metal rod, so that is L0 M. So the temperature difference delta T is a degree per Celsius, and the coefficient of linear expansion of the solid, that is alpha 1 upon degree Celsius. The change in length, that is delta T, of the solid can be calculated as. So delta L is equal to alpha into L0 into delta T. So that is temperature difference, length of difference, then coefficient. So the change in length is directly proportional with the change in temperature. Okay. So the change in length is directly proportional with the change in temperature. So the higher the temperature difference, the higher the increase in length of the material. For example, metal rod. Okay. So the change in length is directly proportional with the change in temperature. So the higher the temperature difference, the higher the increase in length of the material. For example, metal rod. So the length difference delta L is equal with the subtraction of the initial length L0 from the final length L. So delta L is the L minus L0. Okay. So the change in length is directly proportional with the change in temperature. So the higher the temperature difference, the higher the increasing length of the material. So for example, the length difference delta L is equal to the subtraction of the initial length L0 from the final length L. So by replacing 2 in 1, okay, replacing L0. We can calculate the final length. So after thermal expansion, function of the initial length, temperature difference and the linear thermal expansion coefficient, that is L equal to L0 into 1 plus alpha delta T. So the coefficient of linear thermal expansion is not constant but varies slightly with temperature. So therefore the mathematical expression can be applied only to small temperature variations. Okay. So equation 3 becomes L is equal to L0 into 1 plus alpha into delta T. So the coefficient of linear expansion is not constant but varies slightly with temperature. So therefore the mathematical expression can be applied only to small temperature variations. Then next is the thermal expansion of electronic components and MEMS. So the electronic components used in a car are exposed to heat rays due to vibration and extreme temperature changes. Okay. The electronic components used in cars are exposed to high stress due to vibrations and extreme temperature changes. If a car is started, the temperature of the electronic car might pass a value of below 0 degrees Celsius to a value beyond 140 degrees Celsius in a few minutes. Okay, if a car is started, the temperature of the electronic car might pass a value of below 0 degrees Celsius to a value beyond 140 degrees Celsius in a few minutes. So today a big amount of the car recalls by the manufacturers are due to electronic malfunctions. So today a big amount of car recalls by the manufacturers are due to electronic malfunctions. So the thermal expansion is very important for the durability of the electronic components. Okay, so the thermal expansion is very important for the durability of electronic components. So joining of different materials exposed to variations of temperature generates the strain mismatch which can be locally strong. Okay, joining of different materials exposed to variations of temperature generates the strain mismatch which can be locally strong. So these strains might cause cracks which initiate malfunctions. So strain mismatch occurs by the following process. So during the production process, soldering conditions, heat production during curing. Okay, during the production process, that is soldering condition, heat production during curing. Okay, so it is nothing but the thermal expansion of electronic components and MEMS, because electronic components are nothing but highly having the stress due to the vibration and extreme temperature changes. Okay. So during the operation, due to local production of heat, that is resistance losses, microprocessors, diodes, lasers. Okay, so during the operations, due to local production of heat, resistance losses, microprocessor, diode, lasers. So changes of ambient temperature. On the other side, simulations are used in the electronic industry. But the material parameters, that is coefficient of thermal expansion or MEMS modules, have to be known. So a validation of results is necessary. Okay? A validation of results is necessary. So in some cases simulations are not possible, then the measurement of precise deformation is necessary. So in some cases simulations are not possible, then the measurement of precise deformation is necessary. So a coefficient of thermal expansion is the ratio of the fractional change in size of a material to its change in temperature. So a coefficient of thermal expansion is the ratio of the fractional change in size of the material to the change in temperature. So is represented by the symbol alpha, so for solids, and beta for liquids. Okay, so coefficient of thermal expansion for solids it is given by alpha, and for liquids it is given by beta. Then there are uses the silicon unit inverse Kelvin, that is Kelvin per or 1 per Kelvin, or the equivalent acceptable non-SI unit inverse degree Celsius. Okay. So what is the thermal expansion of electronic components and MEMS? So electronic components, for example, supposing a car that are very exposed to high stress due to vibration and the extreme temperature changes. So we can say that the electronic cards might pass to the below 0 degrees Celsius to the beyond 140 degrees Celsius in a few minutes. So the big amount of the car recalls by the manufacturers due to the electronic malfunction. So the thermal expansion is very important for the durability of electronic components. So joining of different materials exposed to variations of the temperature generates the strain mismatch, which can be locally strong. So the strain might cause cracks, so which initiate malfunctions. So strain mismatch occur by the following process. So during the production process, maybe soldering condition, heat production during curing, so during the operation due to local production of heat, so resistance losses or microprocessors diode lasers. So changes of ambient temperature on the other side simulations are used in the electronic industry, but the material parameter like the coefficients of thermal expansion, Young's models have to be known. So validation of result is necessary. So in some cases simulations are not possible, then the measurement of precise deformation is necessary. So coefficient of the thermal expansion is the ratio of the fractional change in size of the material to its change in temperature. So it represented by the symbol alpha for the solids and beta for the liquids, as well as that the unit is Kelvin per or 1 per Kelvin or inverse degree Celsius or inverse Kelvin. So here microsystems are composed of many different types of the structural elements. So here that is wafers for parallel plate capacitors we have seen. Then feathers for accelerometers we have seen. So here the distributed loading, that is bending as well as the axial loading as well as the twisting. So there are many the traces that is combining on that the one material or one plate. So there is a maybe the thermal expansion. So here that the force, then this is width, height, this is the length. So horizontal, vertical as well as in 3-dimensional, that the forces we have to take into the consideration. So the uniform axial stress is alpha is equal to F upon Ws. So if the beam is comprised of a linearly so elastic material, then the strain is sigma is upon E is equal to F upon EWH. That is Hooke's law. So the corresponding change in the length of the beam, that is delta L is equal, differentiation of L is equal to epsilon, that is strain L is equal to FL divided by EWH. So the spring constants for this axial loaded beam can be determined by F is equal to K change in length. So K is equal to EWH divided by L. Then energy methods. So these are methods based on linear elastic behavior and conservations of energy. So that is work done by external forces equals the energy stored in the structure under load, that is energy Q is equal to Fx divided by 2, it's x square by 2. So where F is the applied force, x is the distance moved in the direction of the force at its points of application, and K is the elastic stiffness of the part. So again in the direction of force at its point of application. Okay, so these are methods based on linear elastic behavioral and conservation of energy, that is work done. Okay, so here the chapter number 5 is finished. Thank you.